Hello, everyone. I'm Colin Brady, a PhD student working under Dr. Roy at the University of Washington. I'll be presenting alongside Liu Sao, another PhD student under Dr. Roy, who will be talking to you a little bit later. Today, we're going to be presenting a tutorial on the resource allocation scheme in Mode 2 or off network for NRC V2X and the NS3 implementation of it. This is going to be a higher level of granularity than the previous talk from Tom, more of a focus on the key parameters that exist in CV2X Mode 2 and their effects on the performance in terms of the packet reception ratio. Briefly, the tutorial will be broken up into three parts. First, I'm going to go over the CV2X standards at a high level, and the semi-persistent scheduling algorithm, the distributed resource allocation algorithm for Mode 2 CV2X generally. Then I'm going to talk about the NS3 implementation of those standards alongside some of the issues that remain in the code base. Some of these are going to be my personal opinion, while some of these are going to be existing bugs that I want to highlight for potential users. Then for the second half of section 2, I'm going to pass over the presentation to Liu, who will be presenting at a high level his model for packet reception ratio in Mode 2 CV2X for a simple scenario, which he'll define later, and then showing the results that we obtained through an NS3 implementation of that scenario. There is a URL later that will contain the code needed to generate the raw data, slide 14 for those of you who copy the slides. Then I'm going to go over a more complicated scenario, introducing UE mobility, and show how that affects the results we found in section 2. So let's begin with the CV2X standards. Originally, CV2X was designed to support vehicular networking, broadcasting periodic messages, which is going to be the focus of this tutorial, but it has been expanded to support non-periodic or dynamic messages. Because the network is designed with safety messages in mind, the side link is enabled for direct vehicle-to-vehicle transmissions. These types of safety and status messages are generally considered to be periodic messages, given that they need to be transmitted regularly. The side link was a concept originally introduced for proximity services, a protocol meant to support public safety users. Using the side link, a CV2X enabled UE can communicate in an on-network Mode 1 or off-network Mode 2 modes. In Mode 2, the focus of the tutorial, the UEs use a distributed resource allocation scheme called semi-persistent scheduling, or SPS. To evaluate the performance, there are three key performance indicators: packet reception ratio, or PRR, throughput, and packet interreception time. Today, we're going to focus on PRR, so I'll leave its description to Liu. But packet interreception time is the time between successfully decoding of non-identical packets and serves as a metric related to delay. The mention of non-identical packets will become important later because SPS contains a mechanism to transmit duplicate packets called blind retransmissions to improve decode probability. For this work, we'll be assuming a V2V highway channel model, which is recommended in 37885. And we will further assume that UEs are half duplex devices incapable of transmitting and receiving simultaneously. And because the decoding methodology is left up to the device manufacturer, that nothing like successive interference cancellation or chase recombining is used. Only one packet can be decoded per resource unless otherwise noted, and decoding one blind retransmission is as good as decoding two. So here we can see some use cases and requirements for CV2X as defined by TR 22886 and TS 22186. The table originally comes from a tutorial on NR V2X communications by Garcia et al. Vehicle platooning involves the dynamic formation and management of UEs into platoons or groups of vehicles. Advanced driving is essentially self-driving car or assisted driving type functions. Extended sensors is the ability to exchange sensor data between a number of local vehicles to extend their perception beyond what they themselves can detect. And remote driving is the ability to teleoperate a vehicle in either dangerous or remote environments or where the passengers are for some reason unable to drive themselves. Here we have a glossary for any readers later. So let's start with a more detailed explanation of SPS with the physical scenario. User equipment, or UEs, are distributed along a two-lane road with density rho UE per meter. The UEs are moving at speed v in opposite directions. For simplicity, we'll assume a map collision model. Essentially, if two UEs occupy the same resource at the same time, neither can be decoded. And UEs are sending NSE duplicate packets per transmission out periodically with period TRRI. That RRI stands for resource reservation interval. And here we can see the channel in Mode 2. In frequency, the channel is broken up into subchannels, which are formed from some number of resource blocks defined by the network operator. Each subchannel is split into two parts. The first carries a stage 1 side link control information, or SCI, which is a part of the physical side link control channel, or PSCCH. This piece of the subchannel also contains a physical side link feedback channel, or PSFCH, if that is enabled, but for this tutorial, it will not be. The rest of the subchannel is devoted to the stage 2 SCI and physical side link shared channel, or PSSCH, which is the data of the packet. In time, the channel is broken up into slots. Mode 2 does support numerology. We'll assume the subcarrier spacing is set to the minimum allowed index, so one slot is 1 millisecond. For the rest of the talk, we will call a combination of one subchannel and one slot a physical resource block, or PRB. So here we can see the entirety of the MAC in all its gory details. Don't worry, I'll be going through a more simplified example to explain some of what's shown here in a more digestible format, but there are a few high-level things I want you to take away from this slide. First, because the UE schedules its own resources in a distributed manner in mode 2, there can be collisions. This doesn't even need to be caused by issues like hidden nodes. If two UEs reselect PRBs simultaneously, then they could both select the same PRB and collide. Secondly, like I said before, UEs generate data and transmit periodically. Each time they generate data, they transmit NSE copies of that data on NSE separate PRBs. Third, UEs reserve PRBs for RC transmissions. This is selected during reselection randomly. After RC transmissions, the UE may perform reselection with probability PK. During reselection, the UE is going to, quote, sense PRBs to determine if they are occupied. In practical terms, this means checking the RSRP measured over some known symbol if that is above a threshold gamma SPS. So I'm going to start the explanation of the reselection process with the flowchart and then show an example of this flowchart in action. The process starts when a packet is generated, and if the reselection counter RC is above 1, then the packet uses the existing PRBs and transmits. If it does not, and the UE randomly decides to reselect, probability 1 minus PK, then the SPS algorithm kicks in. There are two phases to the SPS algorithm, sensing and selection. In sensing, the UE first identifies the selection window and corresponding sensing window. The selection window is a set of PRBs that it can select new resources from, and the sensing window is the set of PRBs, one resource reservation interval before. For each PRB in the selection window, the UE checks to see if the RSRP is above gamma SPS in the corresponding PRB in the sensing window, and if it is, it excludes that resource. Then, once all resources are excluded, the UE selects NSE of the remaining resources randomly. The goal of this process is to assume that if a PRB was occupied before in the sensing window, it will be again in the selection window. This makes sense given the periodic nature of transmissions, but in a more complicated scenario with dynamic transmissions or non-cellular users, if the side link were using unlicensed spectrum, this can get a bit fraught. At a channel level, this process appears thusly. The UE with the purple packet transmits until its reselection counter hits 0, at which point it changes PRBs. In this example, the UE always reselects, but that is a function of PK, which can range from 0, the UE always reselects, to 0.8, the UE rarely reselects. We'll explore the effect of that later. You can see here that we've highlighted the second reselection, and we'll show that process on the next slide. In this example, each UE is transmitting with NS equals 1, a good thing given that there are 9 UEs and only 12 PRBs in the selection window, making the channel very dense. We'll also be exploring the effects of NSE later. This slide shows the sensing and selection windows for the second reselection on the previous slide. We can see that the UE makes two types of exclusions. Those in blue are due to the half duplex effect, essentially because the UE was transmitting in that slot, then it did not gather data, and to be on the safe side, it excludes those PRBs. The other set of exclusions, those in red, are due to the previously stated SPS threshold being exceeded. These two exclusions cause the UE to have two PRBs to choose from, the one it chooses in this example, and the PRB directly above that. It's important to note that while the UE we've been focusing on, the purple UE, is performing SPS, so are all the other UEs. Here we highlight another UE and its process while the purple UE is transmitting. Doing a similar thing, excluding the half duplex UEs and those in red, and ultimately making selections. So moving on to section 2, I'm going to start off with a brief description of the V2X implementation in NS3, and then hand it off to Liu to go over his model for packet reception ratio and highlight some of the trends we expect and found through NS3 simulations. My descriptions of the NS3 simulations are going to be brief and at a high level. Hopefully you were able to catch the previous talk by Tom Henderson, where he went into these topics in much greater depth. So packet receptions primarily handled in 3 places: spectrum PHY, UE PHY, and UE MAC. The spectrum PHY is going to deconstruct the packet into its constituent parts and computes relevant PHY effects needed for SNR, SINR, RSRP, interference, and other similar metrics. UE PHY takes the relevant PHY information, converts it into the sensing data object, which is passed to the MAC. These sensing data objects are used by the MAC to perform SPS sensing and make exclusions. For packet transmission, the logic is mostly held in UE MAC and the sidelink UE MAC scheduler simple. The other 2 files shown here, UE MAC and sidelink UE MAC scheduler NS3, really just contain triggers for the main logic. UE MAC handles the implementation of the sensing portion of the SPS algorithm, while scheduler simple implements the selection portion. In terms of the loss and error models, the NS3 simulator uses the models developed in new radio physical layer abstraction for system-level simulation of 5G networks by Lagan et al., which are implemented in various NR EESM tables to obtain BLER from SINR. The MIMO features of the spectrum propagation loss model are in this work disabled for simplicity. The simulation is implemented using an existing example as a base, NR V2X west to east highway. The main changes we've made are various bug fixes, which we're going to highlight in a bit, and some changes to topology, essentially enabling UEs to move in opposite directions and just changing a little bit where UEs are placed. I should also point out, you can also see from the TDD bit pattern and bitmap in the file that we've devoted all the resources to sidelink in this case. Tom went over how to construct that bitmap in his presentation, but essentially you can devote some of the slots to uplink it or downlink or both. We've just chosen to devote everything to sidelink for simplicity's sake. So we reuse the output file format from NRV2X west to east highway, which produces database files you can see here. The main table for most users is going to be PKT-TXRX, which shows the packet transmissions and receptions, which we use for PRR calculations. If the user has NSE greater than 1, then PKT-TXRX will only show 1 packet reception, regardless of how many of the NSE packets were decoded. I would note that while this trace works great for PRR and throughput calculations, the timing information is off. I know it's very small for the viewer in the room, but I've highlighted some pairs of packet transmissions and receptions, and you can see that PKT-TXRX reports different times than the PSCC or PSSCH transmission trace and the PSSCH reception trace. Well, I haven't personally experimented with timing calculations and thus don't know the exact way to fix this. I leave it as a warning to any potential users to be careful with the timing information in these traces. Finally, here we can see some of our analysis code. We use MATLAB to process the database files containing all files, allowing us to extract information on not just PRR, but also collisions, which we'll be showing shortly. Next, I'm going to go over some of my issues with the current state of the V2X code. Some of these issues, like the one on this slide, are my personal opinions and cannot necessarily be forced into the public code base, but I hope that any potential users who are listening may agree with me and I can suggest some simple fixes for these issues. Other issues are existing and known bugs. I have reported all of these to code maintainers, and I'm happy to say that the list of bugs I'm presenting here was originally much longer, with several having been fixed before WNS3. The figure here shows time and RC values of packets transmitted by UE1. Boxes indicate that packets are duplicates. So each pair of packets in one box is a duplicate of each other. The issue is that duplicate packets are transmitted with different reselection counters. That's resell counter, the third column. This issue arises because the standards in 38.321 are written ambiguously, such that it's not clear if the reselection counter is decremented before or after the last transmission. I would say that there's no practical effect on this if RC is not transmitted as part of the packet, which by the standards it isn't. But some have proposed that RC be included in the SCI to enable certain enhancements to SES. In this case, it should be clear that having otherwise duplicate packets with different reselection counters is problematic. If you wish to fix this issue, the simple fix is to change where the decrementation of RC occurs in UEMAC. The next issue with the standards themselves. Something I left out of my explanation of SPS earlier, something that Tom did mention, is that according to the standards, a PRB is excluded if the RSRP is above gamma SPS and a packet was decoded in that PRB. This is quite obviously a very unreasonable condition and has been ignored in this tutorial. Aside from the issues of coexistence and bad actors, the distributed nature of SPS means collisions can happen. A UE should want to avoid a PRB with high RSRP regardless of if a packet was decoded. High RSRP with no packet decode indicates that at least two UEs are already occupying a PRB and they are causing packet decode failures. Why would you want to consider that PRB for transmission? To correct this, there is a simple change, and in our spectrum phi, the condition for adding something to the sensing data object used for calculating exclusions can be changed, so all PRBs are passed, not just ones which are not corrupt. My third issue is that there's no form of energy detection in NS3. If two UEs are 1,000 miles apart, then they're going to attempt to decode each other's packets, although they will fail because they have very low SNR. This is primarily a speed issue, although obviously a practical implementation of C-V2X in mode 2 would need some sort of energy detection or similar detection method. Packets which have no chance of being decoded are still going through that procedure, slowing down the simulation. Similar mechanics exist in the Wi-Fi module and should be ported to the C-V2X module. My last personal issue is that currently the spectrum loss model is hard-coded in 3GPP, is that the spectrum loss model is hard-coded to 3GPP spectrum propagation loss model in NR helper, meaning changing the spectrum loss model can be quite difficult. For me, since I wanted to just use the propagation loss model, my simple solution was to just comment out the main logic of 3GPP spectrum propagation loss model and simply pass the input as the output. That should not be the solution people need to use. For the first of the two bugs I'm going to talk about, there's an issue in NR spectrum phi, which causes the simulator to skip decoding packets when NSE is greater than 1. The issue is the piece of code in brackets here. The offending code is designed to skip duplicate packets if one has already been decoded to speed up the simulation. But something is wrong with the conditioning and the packets can be skipped regardless of whether one of their duplicates have been decoded or not. So basically the idea is, if I send NS equals 2 duplicate packets and I decode the first one, I shouldn't even bother to try and decode the second one because the information is irrelevant. I've already decoded everything. While I'm not sure how to fix the conditioning because I think the idea is good, a quick fix is to simply comment it out. This will cause simulation times to be longer, but the results will be correct. The final bug is that IPv4 cannot support more than 254 UEs. The bug has something to do with a rounding error in an 8-bit number that we think is part of the side link control information, but we don't know exactly why. The reason for 254 is that the first two IP addresses are actually skipped. If you need to use more than 254 UEs, the simple fix is to just skip the two IMSIs in NR helper, which also skips the IP addresses that cause the errors. So now I'm going to hand it off to Liu to cover the model and results and trends for a simple scenario. Before I go on, is there any questions? Before, while we're handing it over?
Colin, there's no questions on the chat.
Okay. Then I'm going to stop sharing.
For Colin? Okay, I'm going to hand over to Luke Howell, who's a PhD student at the University of Washington. Let's switch the video. And down around slide 20.
27.
Okay. All right, and then I believe that this is a little bit flaky.
Just
But when
okay.
when you're
Yeah, I also can.
I'll click on this.
Okay.
I'll show you.
Okay. Thank you, Tom.
Okay.
Thank you, Colin. Hello everyone.
Okay.
Hello everyone. I'm Leo, a PhD student at the University of Washington, supervised by Professor Sumi Roy. So in this section, we will look into the SPS performance, the Mac level SPS performance in a simple scenario. We will use the Mac collision probability and the packet reception ratio to characterize the SPS performance. When we investigate these two metrics in terms of the resource keeping probability PK, UE density NUE, and the number of duplicate packet transmissions NSE. The NSE means each UE will transmit NSE packets in each RI. And in the Mac collision model, we define some collision events. These collision events will be validated by NS3 simulation results. And after that, we will summarize the insights from the model and NS3 simulation. Okay, so we consider a scenario where the UE is uniformly distributed in a line with a certain UE density. And we consider a fully connected network. That means all UEs within the transmission range of each UE. So all UEs can decode packets perfectly if no MAC collision happens or half duplex error happens. So for the MAC collision, we define that if two or more UEs select the same PRB for transmission, then all UEs will fail to decode those packets. Okay, since we focus on pure MAC analysis, so we assume there are no file errors, and the sensing window size is equal to the selection window size, which is equal to a duration of RI. So the number of PRB in each RI. So here, for there are NSC subcarriers, and sense RI, there will be TRI divided by TS slots. So here TS is the slot duration, and TRI is the duration of RI. So there will be TRI over TS slots. Okay. Okay. Thanks. Yeah. So there will be TRI over TS slots in RI. So the total number of PRB in each RI will be NSC times TRI over TS. Okay. Then in a sensing window, UE will know which PRBs have been occupied. Then UE will obtain the available PRBs by including those occupied PRBs. So in the selection window, UE will know which PRBs are available, and we assume that those available PRBs are assumed to be unoccupied. And then UE will reselect one of available PRBs in the selection window with probability 1 minus PK, or UE will stick with the current PRB with probability PK. Well, we consider a single case where RC is decremented synchronously. So for example, at T1, we consider three UE case. So at T1, both UE0 and UE1 RC is equal to 1. Well, the UE2 RC is equal to 10. After 1 RI at T1 plus TRI, then all of the RC will be decremented by 1. So UE1 RC and UE0 RC will be 0. Well, the UE2 RC will be 9. So then after 1 RI at T1 plus T2 TRI, UE0 and UE1 will, so because in here at T1 plus TRI, UE0 and UE1 will enter the selection window. Then UE0 and UE1 will initiate RC, which ranges from 5 to 15. So at here, UE0 and UE1, so UE will initiate RC equals 9, and UE0 will initiate RC equal to 12. And then because for the UE2, it hasn't decremented to 0, so it's just decremented by 1, and the RC will be equal to 8 at T1 plus T2 TRR. Okay. So now we start to analyze the MAC collision probability. So again, the MAC collision happens if 2 or more UE transmit in the same PRB. Then all UEs will fail to decode any of the overlapped packets. Well, the MAC collision event always start in the selection window. So first, when reference UE, we denote a UE0. When UE0 RC decrements to 0, then UE0 will enter the selection counter. Well, a collision may happen in the selection counter. It depends on the behavior of UE0. So first, if UE0 perform reselection in the selection window, then a collision may happen. We define such a collision as collision event 1. And if UE0 doesn't perform reselection in the selection window, a collision may also happen. And we define such a collision as collision event 2. Well, when the MAC collision happens in the selection window, it always followed by a consecutive collision, and we will talk about later with more details. So the total MAC collision probability in the selection window will be sum of two collision probability. So we denote the probability that collision event 1 happens as Pico 1 and probability that collision event 2 happens as Pico 2. So let's first start with the collision event 1. So again, when UE enters the reselection, so the collision event 1 happens when UE performs reselection in the selection window, and then the collision happens. So first, when UE performs reselection with probability 1 minus PK, PK is a resource keeping probability. So UE performs reselection with probability 1 minus PK. Well, so at T1 plus 2 TRI, UE0 RC decrement to 0. And well, at the same time, another UE1 RC decrements to 0 at the same time. So that means UE1 also enters the selection window. And well, if the collision happens if UE1 perform reselection in the overlapping selection window, if UE1 and UE0 select the same PRB, among the available PRBs, then the collision happens, right? So we define this collision as collision event 1. So at T1, at the end of the selection window at T1 plus T3 TRI, UE0 will initiate RC value, which is equal to 9. Well, UE1 also initiate RC value, which is equal to 12. So because after RC is set, then this PRB will be reserved for RC initial RIs. So there will be, so in this case, there will be 9 consecutive collisions right after the overlapping selection window. So because our initial RC value ranges from 5 to 15, so there will be the minimum of 2 RC initial values consecutive collision happen right after the selection window, right? Okay, let's now focus on the collision event 2. Yeah, so collision event 2 happens when UE doesn't perform reselection in the selection window with probability PK. Well, this collision happens conditioned on 2 UEs has collided with each other in the prior RIs. So this, so here we can say when RC when UE0 RC decrement to 0, so both UEs will still collide in the UE's current selection window, but in the prior RIs they have collided with each other. Yeah. So, but this collision happens due to the collision event 1. So previously there must be a case that UE0 has collided in UE1 due to collision event 1. Then the collision event 2 will happen in here. Okay, so so actually the collision event 2 can be divided into 2 sub events. It depends on the collided UE's RC state when UE0 RC decrement to 0. So for sub event 1, so when UE0 decrement to UE0 RC decremented to 0, and the other collided UEs RC also decrement to 0 at T1 plus 2 TRI, right? So then UE1 doesn't perform reselection in the overlapping selection window, and both UEs will stick with the same PRB. Since these 2 UEs has collided in the prior RIs, so in their overlapping selection window, the collision will still happens, right? So because at the end of their selection window, both UEs will initiate the RC, initial RC, because their RC ranges from 5 to 15. So the number of consecutive collisions will also range from 5 to 15 right after the selection window. All right. Okay. So another sub event when collided UE haven't decrement to 0 when UE's RC when UE0's RC decrement to 0. So in this case, UE1 will still use the previous reserved PRB in UE0's selection window. Yeah, but UE0, because it doesn't perform reselection in its selection window, so the collision will still happen in this case. So here the number of consecutive collisions is different from the previous case because so at the end of the UE0 selection window, UE will initiate RC, which ranges from 5 to 15. But for UE1 here, it only ranges from 0, right? Because it depends on previous value. So at T1 plus 2 TRI, it ranges from like 1 to 15. And here, yeah, when after 1 RI, the RC for UE1s will range from 0 to 14. So when we take the minimum value of these two, so the number of consecutive collisions will range from 0 to 14, right after a UE selection window. Okay. Okay, now we focus on the packet reception ratio, which depends on the MAC collision errors and half duplex errors. So again, MAC collision errors happen if two UE transmit in the same PRB. Well, the half duplex error happens because the vehicle is the UE is enabled to transmitting and receiving the same slot. So it depends on the number of slots in a RI. So because TRI over TS is the number of slots in a RI, so we just reverse it. So this is the probability that the half duplex error happens. So we should note that the MAC collision error is much severer than the half duplex error, because if MAC collision error happens, none of UEs will receive the packet from the transmitter of UE. But for the half duplex error, if one UE transmits in the same slot as the reference UE, only that UE cannot receive packet if no MAC collision happens, right? Now there are two cases for NSE. Remember, NSE is the number of packets sent in each RI. So if NSE equal to 1, the packet can be received successfully if both errors do not happen. So we can calculate the PR is equal to 1 minus collision probability times 1 minus PhD. Well, when NSE is greater than 1, this packet received successfully if at least one of duplicate packets received successfully. So here, this means the inner term represents the probability that one packet is received unsuccessfully. So this whole term means the probability that none of the duplicate packets received successfully. So 1 minus this term will be represent the probability that at least one of duplicate packets received successfully. Okay, so let's go to the NS simulation result. So this slide shows that the simulation result for the fully connected network, because we previously I showed that the UEs are uniformly distributed in a line. So and in our simulation, the inter-UE distance is just 1 meter. So we can say so here, if there are 200 UEs, so here at 0, this is what the reference UE is located, and here is the last UE, the last UE in a simulation. So because the inter distance is 1 meter, so we can span the 200 meters in simulation. So for 100, if there are 100 UEs, we can see the last UE will located at 100 meter. So we can say that in a fully connected network, the PR, there is no distance dependence on PR, right? Okay, so let's focus on the impact of PK on the MAC collision probability. So we can say under the low PK case, the PK1, the collision probability that collision event 1 happens, dominate the total collision probability. When PK increase, the PK1 decreases significantly. Yeah, and the PK2 increases slowly. Yeah. So then we can see that the total MAC collision probability will decrease when PK increases. So this is because when PK increases, the behavior of the behavior of transmitter UE will become more predictable to other UEs, right? Because the transmitter UE will perform less reselection in the selection window. Right? Okay. So with that, we check the collision event, each collision event on the different PK case at different NUE. So when NUE increases, the overall collision probability increases. So we notice that at PK equals 0, there is only one line because there is no, because UE doesn't perform because UE only perform reselection in the selection window. So there only exists Pico 1. So here Pico will be equal to Pico 1, right? So under PK equal to 0.8, yeah, there should be the Pico 1 and the Pico 2 and the total collision probability. So the total collision probability will be sum of Pico 1 and Pico 2 under PK equal to 0.8. Well, this slide shows the impact of PK on NA. The average NA is the available the number of available PRBs in the selection window. Yeah, so the number of as I mentioned before, the number of available PRBs is the total number of PRB minus the occupied, minus the number of occupied PRBs. So we can say that so for giving NUE, we can say that the average NA with PK equal to 0 is higher than that with PK equal to 0.8. So this is because for giving NUE, the collision probability with PK equal to 0 will be higher than the PK equal to 0.8. So for PK equal to 0.8, UE will occupy more available PRBs to lower the collision probability. That means the average number of available PRBs will be less than PK equal to 0. So for example, so if NU is equal to 100, and if so for PK equal to 0, if there are 10 UEs collided with each other, so there will be 90 occupied. There will be 90 PRBs and 10 UEs. And if we consider each collision only involves 2 UEs, so there will be 95, right? 90 plus 10 divided by 2, 95 occupied PRB. But for PK equal to 0.8, if we consider, if we have like five UEs colliding with each other, and we also consider each collision only involves 2 UEs, so there will be 95 plus 0.2 occupied PRBs. So there will be 97.5 PRBs occupied. So the average, when we use the total PRB minus the occupied PRB, we can say that the average NA with 0.8 will be less than that with PK equal to 0. Okay, so here is the RPRI in terms of NUE. So it's not surprising that when NUE is increasing, because there are more UEs occupy the channel. So there are much higher chance that UEs will collide with each other. So when NUE increases, the PR will decrease. And because the collision probability with N0 with PK equal to 0 is higher than PK equal to 0.8, so the PR with PK equal to 0.8 will higher than the case with PK equal to 0. Okay, so we now focus on the effect of the impact of NRC on the collision probability. So we can say that when we at a given NUE, when we increase the NSE, so NSE is the number of packets in each RI. When we increase NSE, the MAC relation will increase, right? Because we can assume that there are more UEs in the participate in the reselection when NSE increases. So we can say, for example, for when NSE is equal to 100, and we can say at NSE equal to 2, it should be approximately equal to the collision probability at here, right? Because when NSE equal to 1 at NUE equal to 200, there should be 200 packets in each RI, and at here there also should be 200 packets in the channel in each RI, right? So these two collision probability should be approximately equal, right? Okay. Yeah, we focus on the impact of NRC on PR. So we can say so under different NUE, when increase NRC, the collision probability will with NRC equal to 2 is always higher than the collision probability with NRC equal to 1. But we have different results regarding the PR. So at the low vehicle density, we can say that the PR with NRC equal to 2 is higher than NRC equal to 1. But at the high vehicle density, this will be inverse. Yeah. So we can say we can explain that this result. So we can say when NUE times NRC is less than the total number of PRBs, we say that when increase NRC, the collision probability will increase, but the PR will also increase. So if we ignore the impact of half duplex, the PR, which is a function of NRC, should be proportional to 1 minus pico to the power of NRC. So remember that the packet is received successfully if at least one of the NRC received. So when we add the power of NRC, the pico of 1 will be greater than the pico of NRC to the power of NRC. So let me give you an example. So here at the under saturated condition, so pico 1, let's say it is equal to 0.3, and the pico 2 is is equal to 0.5. So we will plug into here. The PR in NRC equal to 1 will be 0.7. Well, this one 1 minus this will be 0.75, right? So then the PR with NRC equal to 2 is greater than the PR with NRC equal to 1. But if in the oversaturated condition or in the saturated condition, when NRC increases, the collision probability will also increase, but the UE cannot benefit from PR when increasing the NRC, because let's give an example. So if pico 1 is equal to 6 and pico 2, pico of 2 is equal to 0.8, then we get pico of 2 square is equal to 0.64, right? So in this case, the collision probability, the PR in here will be 0.4, and here it will be 0.36. So yeah, so the PR with NRC equal to 2 will be lower than PR with NRC equal to 1. Yeah, actually, we can also find this cross point if we look at the previous slides. Yeah, because when NRC equal to 1, here is the expression for the PR expression for s equal to 1, and when s equal greater than 1, here's the total expression. And if we set this one PR of 1 equal to PR of 2, right? Because we haven't know the NSE, we haven't know the collision probability of NSE with a certain NSE and PK. We just solve this in UE, right? And then we can find the cross point. The cross point is the cross point indicates the number of UE when the UE PR in 2 cases are equal, right? Okay. So here we next focus on the impact of PK on the NC. The NC, here average NC means the average number of packets in each collision. So at low UE, because there are not much UE in the RI. So when a collision happens, there will be only 2 UEs, right? Almost 2 UEs in each collision. But when NUE increases, well, more UEs will be likely to select the same PRB. So yeah, so the number of average packets in a collided PRB will be more than 2. Right? And we also, count we'll get to the ratio of number of UEs in each collision. So in most cases, no matter in a low vehicle density or high vehicle density, low UE density or high UE density, the two-way collision always dominate the MAC collision events, right? Okay, so let's summarize the insights from our model and NS simulation results. So in the undersaturated condition, when we increase the number of duplicate packets, the PR will increase. While under the oversaturated condition, the UE cannot benefit from increasing the NSE, right? And then when we increase the PK, then the collision probability will decreases. And then the PR will increase. This is because when we increase PK, the behavior of the transmitter becomes more predictable because UE will perform less reselection in the selection window each time. And there's no trade-off in a fully connected network. So if UE if we consider mobile scenario, UE will enter or leave the fully connected network. There should be an optimal PK for giving rate of change. And Colin will talk about more details about this part. Well, the last part is the collision always happen consecutively after the when MAC collision happens. It will last 1 to 16 TR. So if the duration of RI is equal to 100 milliseconds, so the consecutive collision will last to 100 to 1600 milliseconds in SPS. So that means the time-sensitive applicants, such as basic safety message, may suffer from kind of consecutive collisions. Yeah, that's it. Yeah.
Questions? So I have just one question. What is the reason in your model for distinguishing between what you call a half duplex error and a MAC collision? Isn't a half duplex error basically a MAC collision, but you happen to be one of the reads involved?
Well, because if we consider the PR, we need to consider both. Yeah. So because we focus on MAC, pure MAC layer. Yeah. So if
is this for the PRs you're showing?
A PR showing
PRs with respect to just a single local node, or is this globally in the simulation?
We just track one UE in the global network. So
the PR is just one of the many units.
Yes.
Okay.
Any question? Okay.
Yeah. So can remember the other slide that had this consecutive collisions. Yeah, this one. Do you have any kind of I guess data on what the distribution of those consecutive collisions are? Like, is it largely one time step collision and occasionally the 16 consecutive slots of collision, or how is that distributed?
Yeah, we haven't do that step. Yes, I think it's a good suggestion. Yes, but yeah, we can see. Yeah, maybe we can focus on the previous slides. Yeah, I think we can count the different scenario. Well, like so when collision event one happens, so in this case, I think we can actually calculate the probability, but we haven't tracked that. Yeah, but we can calculate the number of consecutive collisions in each collision event.
Yeah.
Yeah. Thanks for the suggestion.
But either way, some of the collision events, you're going to get successive collisions, even if you have the reselection of all these reselection. Right?
Yeah.
It's just going to be something between 0 to 15 all the time.
Yeah.
So, right. So it'll be some distribution between
16
or 0 to 15.
Yes. Yes. Yes.
Liu, can you please stay closer to the mic, and do you mind restating the questions, because people in the online audience are having trouble hearing?
Okay.
Yeah. Repeat the question about this.
Okay. So the question is, so can we get the distribution of the number of consecutive collisions? Yeah. So yes, so we can. So mostly the number of consecutive collisions went from 0 to 16. Yeah, and yeah, we can. Yeah, mostly happen. Yes, but I think the number of consecutive collisions could be greater than 16 if if two UEs still stick with the same PRB, then the collision will happen. But that it will happen less often than this case. Any question? No, I will hand it to Colin. Yeah.
Can you stop sharing? Okay, sorry for the speeding through this. Just getting back to the correct point. Okay. So thank you, Liu. Next up, we are going to make this situation a little more complicated by adding in mobility. So just as a refresher, for these simulations, we have UEs in 2 lanes moving opposite directions at speed v. For these simulations, we'll be using a phi collision model, where if 2 or more UEs occupy the same PRB, then 1 can be decoded if it has sufficient SINR. So that's a difference from the previous simulations where it was a map collision model. So why are we talking about mobility? The answer is that mobility allows us to introduce the notion of the underlying topology, that is the positions of the UEs during the simulation, changing over time in a simple way. Here we can see a simple example where at T1, the black UE is in one position with the packets of 3 UEs being decodable, while at time T2, it's in a different position with 3 different UEs being decodable. If T1 and T2 are close enough that the black UE did not reselect between those 2 times, then its PRB choice might be bad and cause a collision. You can see that happening here, where at T1, the black UE's PRB choice is good, given that it avoids the other 3 UEs it can detect, while at T2, suddenly it collides with the blue UE, whose transmission it did not consider because it could not sense it during the last reselection event. Essentially, it was hidden to the black UE. In addition to that, we are going to be simulating over much larger distances, meaning there will now be hidden nodes, so more chances for collisions. Before, collisions can only occur if 2 UEs are reselecting at the same time. Now they can occur because there's hidden nodes and you don't know what they're doing. So what do we expect to happen now? In terms of NSE, the trends should be identical. At low UE densities, NSE will, a higher NSE will maximize PRR, while at higher UE densities, lower NSEs maximize PRR. This type of behavior would benefit from an algorithm to tune it during runtime, but that's outside of the scope of this tutorial. PK is a more interesting parameter for mobility. For the fully connected topology, where there were no changes to topology over time, higher PK was always better because reselecting less often made you more predictable, making it easier for others to avoid colliding with you. In a technical sense, when you perform reselections, you open yourself up to collisions because other UEs can reselect simultaneously. If you don't reselect, other UEs should know to avoid your PRB because it's occupied. But with mobility, there's now an added element where over time, you are now able to sense more and more UEs you could not sense previously, meaning they were hidden to you during your last reselection event. And therefore, you are more likely to collide with them. This creates a trade-off where at high speeds, you may lose more to increase collision probability than you gain from being more predictable. Here, we can see the implementation details for our simulation scenario. The road is simulated as a single path where when UEs reach the end, they're teleported to the other side. Because, meaning that they're just sort of moved from one slot to the next, from 0, 0 to the other boundary in one slot. Because UEs near the edge of the road can sense up to half as many UEs, UEs in the outer regions are excluded from the analyzed data. We'll explain in a bit how we determine the boundaries of those edge regions and the total track length. We implemented this mobility model using constant velocity mobility model as a base, creating a new function, constant velocity helper, to perform this teleportation as shown here. Again, all of this code is available in the link that we provided before. To determine the bounds of these simulations, we first experimented with finding PRR when collisions are not a factor. So only phi errors are a major contributor to decode failures. We did this by placing two UEs at varying distances and measuring the PRR over 5 minutes of simulation time. You can see from our plot of PRR that after about 800 meters, UEs can no longer decode packets. With this, we selected 800 meters for the edge of our simulations as the bounds, the outer region alongside with 1,000 meters for the inner region for a total track length of 2,600 meters. This is compared to a maximum 200 meters for the fully connected network. I would note that the fully connected network simulations also use a larger transmit power than we're using for this, causing the curve shown here to not be representative of the bounds on decoding packets for those simulations. Next, we're going to show the logic for the bounds of the variables we used in terms of dV, the distance between UEs, and the stand-in for UE density and speed V. To do that, I'm going to use a simple model for decoding where if two UEs are less than a decode distance DD, then they can decode each other's packets probability 1 and 0 otherwise in the absence of interference. DD is then the average distance of decoded packets, and based on our curve of PRR, it's approximately 350 meters. Just to make really clear, this is not something that's in the simulation. This is really just for this sort of math to understand the bounds of these variables and what they mean. With DD, we can compute the number of decodable UEs with ND as 2 times DD divided by the distance between the UEs rounded down times the number of lanes. With ND, we can calculate how saturated the channel is. We define this value as the number of decodable UEs times the number of packets they send, NSE, divided by the number of resources in the sensing window or selection window, NR. Essentially, packets divided by PRB. For these simulations, we use NR equals 50. We further define levels of saturation as shown on this slide and select some values for DV, which meet those categories. Based on these calculations, we selected DV equals 20, 40, 60, 80, and 100. With ND, we can also compute how quickly the underlying topology changes. For this, we define the metric as the number of new decodable UEs within DD after 1 second. 1 second is the amount of time between reselection events or potential reselection events. Regardless of how you select the resource reservation interval, because the expected value of RC always changes based on that choice to make the expected value of RC times TRI equal 1 second. Note that for this simulation scenario, our metric cannot exceed 0.5 because the UEs in the same lane as the reference UE are moving at the same speeds. They're always going to be within that decode region. With our metric, we find a set of speeds to test to be 0, 125, and 250 meters per second. Now, if you're thinking to yourself, 250 meters per second is about as fast as the cruising speed of a passenger airliner and seems quite a bit faster than my Ford Taurus, you would be correct. So I'll say that first, these speeds are really here to be a proxy for topology change, and how fast we need the UEs to move to achieve high speeds is a function of a lot of things. For instance, if the channel were much harsher and DD were much smaller, then the max tested speed would be much lower. But more importantly than that, this is a tutorial, and we're exploring the required rate of change needed to see trends for the fully connected see new trends from the fully connected network. If you, as a network designer, feel that no practical deployment would experience such rates of change, then you can ignore those extreme points and consider trends at more realistic speeds. Before showing results, we need to cover how we're displaying the data. As you can see on the left figure, the PRR is now a function of distance between the transmitter and receiver distance, DTR. So the simple averaging we did for the fully connected network needs to be addressed. For the rest of the slides, we'll use averaging shown here, averaging over the first 800 meters in this case. The value that you use for the endpoint of the averaging isn't important as long as PRR is approximately 0 at that distance, which it is in this case. With the averaging, you can see the 3 distance-dependent curves transform into a single average PRR curve on the right. Here, we're showing the effects of the number of blind retransmissions, NSE, and speed V on the packet reception ratio. First, commenting on V, you can see that V is not a major factor as a function of UE density. Speed does change the PRR primarily through differences in the error model at various speeds, but not enough to change trends. In terms of NSE, we see the same trend as fully connected networks. At low density, high DV, NSE equals 2 provides higher PRR, while at high UE density, low DV, NSE equals 1 provides higher PRR. Like for the fully connected network, this occurs because at low UE densities, the channel is underutilized, and increasing the load by increasing NSE gives greater gains from repetition coding than losses from increased collision probabilities. At high UE densities, that effect is the opposite. The losses from increased collision probability is greater than the repetition coded gains, as the channel is already oversaturated. Finally, we show the effects of probability of not reselecting PK and speed V on the packet reception ratio. We can see that, like the fully connected network, in the static case, higher PK is always better, leading us to believe that the addition of hidden nodes alone does not change this behavior. But as speed increases, we can see that PK equals 0.8 starts to decay in performance at V equals 125 before totally collapsing at V equals 250, where PK equals 4 becomes the best. As previously stated, there is a trade-off between rate of reselection and rate of changing the underlying topology. Reselection introduces an opportunity to collide because other UEs in your local region could also reselect simultaneously, and both UEs could select the same PRB. By reselecting less often, this probability is minimized. But when your speeds are high and UEs which used to be hidden to you during your last reselection cease to be hidden, those UEs can also cause collisions, as shown on slide 47. If the UE doesn't reselect once that has happened, it causes performance degradations. We can see here that the point at which the losses exceed the gains requires a very high rate of change in the underlying topology. Lastly, we've summarized here the main findings of the simulations we've shown throughout the presentation. I won't repeat all of this, but I'd just like to take the opportunity to highlight a few key points. First, I'd like to thank the developers of the NRC V2X module. I think that overall this is a very good simulation tool that can be used to learn a lot about NRC V2X, and I appreciate responding to and fixing the niggling issues that exist in the code base. Next, there are a number of key knobs which affect the performance of NRC V2X, which we've covered today. NSE, the number of blind retransmissions, is a big one, which affects the packet reception ratio, and by extension, the throughput. The range of UE densities over which NSE affects the PRR should lead network operators to implement some algorithm which tunes this parameter over time. Just setting and forgetting could potentially lead to big losses in throughput. As for PK, tuning is much less needed. As we've shown, the only speeds at which the max PK was not optimal are very unrealistic. In all likelihood, setting this parameter to 0.8 and leaving it there should be sufficient. Finally, the standards could use a bit of work. Most of the remaining issues I have with NS3 are really issues with the standards, as I can't expect the developers to implement things outside the standards arbitrarily. I am aware of some movement on implementing LTEU, or the unlicensed LTE standards, which would solve my issues with lack of energy detection mechanism. But I believe that the sensing assumption, only excluding TRBs with decoded packets, is incredibly restrictive, harms performance, and does not gel with unlicensed bands V2X may well be operating on. So thank you for attending this tutorial. Are there any questions?
I don't see any in the chat. Any questions in the audience? So you go ahead, Richard.
Yeah. Do you have any plan to look at the coordinated sensing where you share information about their sensing to improve the performance?
Colin, did you get that? And can you repeat
No,
it?
you need to repeat the questions.
Sorry, can you or why don't you take a link?
Do you have plans to look at the coordinated sensing where you share information about what they see to improve the performance?
Not as of this point. I think that there's a lot of directions for future work on this. I think that that's one of them. Another big one is to think about unlicensed bands or sort of coexistence environments.
Yes.
Yeah. In the past loss model, the 37, I believe, 385 has lots of options. How many options are coded in the NS3 model?
So the question is, how many options are of 37885 path loss are in the NS3 model? You want to answer?
I believe the answer is all of them. I know V2V highway and V2V urban are. Offhand, I don't know. I think it's all of them, but definitely V2V highway and V2V urban.
There's urban and rural, macro and micro, if I remember correctly.
Okay.
And I believe all 4 path loss models are coded.
Yeah.
I'm not sure about what support for the fast fading differences offhand, but this is all the current model is using the 3GPP propagation loss model, which is in the mainline NS3, which is heavily documented if you check the propagation model there. Any other questions? Yes.
In the model, in the grid structure, they assume that it's sort of parallel, like lanes and stuff, adjacent, sort of more fully defined. Does the model include some sort of haphazard sort of switch crossing and not in a regular pattern? And would that be something that the loss model would kind of have out of adjacent rather than just once defined in the specification?
Sure. So the question is that the model that you showed was very regular 2-lane. And could it, I guess the question is, could it be extended, or have you considered variations where there's hazards or cross streets or divergence from this uniform grid pattern?
Sure. I mean, the answer is that you can make it as complicated as you like. If you want to, I mean, the point of this tutorial is to be a teaching example. And so I thought a very regular, simple 2-lane road was sort of the most easy to grasp. But you could input a cross street if that's what you wanted to do, or I don't know how you would necessarily input sort of hazards aside from predefined turns in the road. but NS3 has the capability, broadly speaking, to do any sorts of mobility that you need. If you wanted to do something like not straight roads, you'd probably need to make use of the waypoint mobility model as opposed to constant velocity. Constant velocity really is just for straight lines.